Welcome back. In this lecture, we're going to discuss the MNIST dataset. Before we actually get started with convolutional neural networks and Keras, I want to quickly take a brief moment to really understand this classical dataset. And if you've ever had any other course or even read a book on deep learning, you've probably already encountered this dataset before. It's super famous in the field, especially in convolutional neural networks and deep learning. I want to quickly cover some basics about it since we're going to be using really similar data concepts, specifically the way we organize these data sets into four-dimensional arrays. So since we're using that idea quite frequently throughout the course, I want to just briefly cover that. Okay, now for this particular data set, fortunately it's really easy to access with Keras. You just upload it with a built-in function in Keras, and it has 60,000 training images and 10,000 test images. Right off the bat, you can tell that it's a huge data set. And the MNIST dataset, in case you're not familiar with it, it contains handwritten single digits from 0 to 9. So here we see some examples of all the different ways people draw zeros, ones, twos, threes, and so on. Now, as you may imagine, a single digit image can be represented as an array. So specifically, in this dataset, the arrays are 28 by 28, and they're just pixels, where the value of 0 represents white, and the value of 1 represents black. So these values are grayscale, meaning we only have a single color channel. And also important to note here is that it's been standardized or normalized. So you can see all the values fall between 0 and 1 instead of values from 0 to 255. That's really going to help our neural network learn on this particular sorts of data sets. So often when we're working with image data, we will normalize things to fall between 0 and 1. This data set already has that step for us. Now we can think of the entire group of 60,000 images, or for the test set, 10,000 images, as a four-dimensional array. And it's 4 dimensions because we have the dimension for all the images, the dimension for the color channel, in this case it's 1, and then the dimension for the x and y, 28. So we have this really large 4-dimensional array, and so it's going to have 4 dimensions of 60,000, 28 by 28, and then 1. So we have the samples, the x and the y, and then the number of color channels. In this case, we have just a single color channel because it's grayscale, but for color images, that last dimension value would be 3 because we'd have one value for red, one value for green, and then one value for blue, all standardized between 0 and 1. Now for the actual labels, we're going to use something known as one-hot encoding. This means that instead of having categorical labels such as strings of 1, 2, etc., we'll have a single array for each image. Now, the original labels, when you upload it in Keras, they're actually given as a list of numbers. So if the very first image is a drawing of the number 5, then its corresponding label is just the digit 5. And what we need to do is we need to convert that to one-hot encoding. Again, this transformation is actually really easily done with Keras, but I want to make sure that we understand what's happening behind the scenes. So what happens is the label is represented based off the index position in the label array. The corresponding label will be a 1 at the index location and 0 everywhere else. For example, if you happen to have a drawn digit of 4, then it would have this particular label array. Notice that index 4, so 0, 1, 2, 3, 4, that is one-hot encoded to be a 1. And the reason we use this one-hot encoding is because it works really well with a single layer output where we have 10 neurons, and then each of them is triggered to fire with a sigmoid to either 0 or 1. Now, as a result, the labels for the training data ends up being a really large 2D array. So we end up having 60,000 by 10 because each of those labels is now an array of 10. And in case this image isn't really clear, when we actually see it in NumPy, it looks something like this. So here's our Y train, for instance, and we have all these one-hot encodings. So that means if you look at the second row, that number, its label is 0 because it's one-hot encoded at 1 at index 0. And for some of these other ones, it deleted, well, it has an ellipses for the middle value, so we can't quite tell. Okay, so now that we understand the MNIST dataset and one-hot encoding, let's apply our new knowledge of convolutional neural networks with Keras on this dataset. Let's get started. I'll see you at the next lecture.